Okay, what we're looking at here are empirical equations, and when we talk about empirical equations, we're really just talking about functions. New functions where we're going to put in numbers and get answers. If you haven't watched the function video yet, I really recommend you do so. Maybe you want to do it on an empty stomach, but it's definitely a good video to start thinking about functions and what we're talking about here. Okay. Now, what empirical equations are doing is we're taking some function, but we're creating that function out of an experiment involving measurements, okay? Because of this, though, our answers have to be rounded according to sig fig rules, and we have to make sure we're using our units properly. So let's take a look at an example of a function from an empirical measurement, okay? Our function here is describing how much fuel is used by a car engine dependent on the speed of the car, okay? Fuel is given by the variable f. Remember, a variable can be anything. It's just some space holder for a number for later on. And our variable for the speed is s. So what we're really looking at here, if we kind of think about it, is we're looking at a function where depending on the speed of the car, we're going to be using so much fuel, okay? Speed is the input to the function, and the amount of fuel is what we're finding on the output. So if we're calculating the amount of fuel used when the speed is 45 kilometers per hour, this right here is the speed variable. This is s. And we're just going to substitute it in right here for the variable. We are not going to sub it in for the units here. These are units. We're going to end up canceling things out in a second. This 45 kilometers per hour is a speed. It is this variable s. So to do this, we're looking for fuel, so F equals, and then we've got the rest of this here. This 0.76 is some coefficient in front of things, so 0.76, and I'm going to write this as milliliters per kilometers per hour. If you remember in a previous video when we were talking about dimensional analysis, I don't like to write things with this slash because I find that a lot of people mess things up when they do that. I like to write them over one another. And the reason why we write them over one another is now when I multiply it by the speed, which was 45 kilometers per hour, 45 kph, I can easily see now that this kilometers per hour in the numerator and the denominator are going to divide out. And then you need to add the 1.4 milliliters here. If you actually take a look at this equation, it's actually interesting to look at because it's really y equals mx plus b. This m, this 0.76, is the slope here. This y is our fuel, which we saw over here on the graph. And this x is the speed, and b is our y-intercept. So if we actually wanted to graph this, it would look something like that, right? Where the slope here is 0.76, and this point right here is 1.4. Okay, so that's what's going on here. The other thing that's nice is because there's an addition here, m times x here will give us milliliters, and we're adding milliliters. Whenever you add things together like that, they have to be the same units. So if we do this, we know what we want to do here. It's just a matter of multiplying and then adding and keeping track of sig figs. So when we take 0.76 times 45, what we're going to get is both of these have 2 sig figs, so when we multiply this, we're going to get 34 milliliters, and we have to add that to 1.4 milliliters to equal our fuel amounts. You want to be careful here. I wrote it left and right, but if we think about the buzzsaw, this is going to be 34 and 1.4 that we're adding together, and if we buzzsaw this, we're going to get 35.4 here, and that 0.4 is going to go away on the buzzsaw. So our final answer here is just 35 milliliters, okay? If we wanted to do this backwards, okay, if we wanted to figure out the speed when we know how much fuel is used, it's a very similar thing. We still use the same equation, f equals 0.76 s plus 1.4, but now we know the fuel and we're looking for the speed. So now this fuel amount here will go in for f. 25 milliliters equals 0.76 milliliters per kph times s plus 1.4 milliliters. At this point, you now just have to perform a little bit of algebra for this. If you feel great about your algebra, awesome. Run it and get yourself an answer. If you're like, ooh, my algebra, well, then follow along and we'll figure this out. What we have to do first, though, is subtract the 1.4 milliliters from each side. So the 1.4 is going to go away. When I subtract the 1.4 here, I do need to remember the buzzsaw. So I would get here, let's see, that's going to be 23.6, but then I buzzsaw, so I just have the 23, but then it rounds up. So I'm going to have 24 equals 0.76 milliliters per kph times S. And then what I need to do is I need to divide each side by the 0.76. So I'm going to have 24 milliliters divided by 0.76 milliliters per kilometers per hour. When I do this, it's important to remember that when you divide by a fraction, it's like multiplying by the reciprocal. So these milliliters are actually going to go away because it's like saying milliliters over 1 times kph over milliliters. So the milliliters go away. My answer will be in kph, kilometers per hour, which is a speed that I'm looking for. So I know my answer is going to be right here. Both of these have 2 sig figs in them, so I can just take 24 times 0.76. I get 18.24. I only keep the first 2 sig figs of that, so I'm going to get, wait, did I multiply? Oh, I multiplied. I should get a larger number here. 24 divided by a decimal should give me a number. 24 divided by 0.76. I get 31.57. I only keep 2 sig figs, so that's 31, but the 0.5 caused me to round up. So I get 32 kph as my final answer. Okay, so that's how we go about doing that. I'm going to pause the video for a second. Take a minute, see if you can do the second one here. It's just a new formula, a new function with mass and a radius of a disk, and see if you can work these out. Okay, so pause the video, see if you can work them out, and then I'll work them out real quick and you can see if you got the right answer. Okay, pause. Okay, so let's work these out now. Radius is 2 centimeters, so mass equals 5.3 grams per centimeters squared. That should be a squared there. Times the radius, which is 2.0 centimeters squared. So what's going to happen is this is going to square and become 4.0, but this is going to be centimeters squared. So the centimeters squareds are going to cancel. And we're going to get 5.3 grams times 4.0, which gives us an answer in grams, which is nice. 5.3 times 4.0 is 21.2, but I only have 2 sig figs, so this is going to be 21 grams. For the other one, we're calculating the radius here, which we got to be careful about because that's squared. So if I wanted to calculate the radius here, and our mass is 8.5, so that m is going to be 8.5. This is going to be 8.5 grams equals 5.3 grams per centimeter squared times radius squared. Now, if I want to solve for this r here, I got to get rid of the 5.3 grams per centimeter squared, and since they're multiplied, I need to divide. So I'll divide each side by 5.3 grams per centimeter squared. Those will go away. So I've got 8.5 grams divided by 5.3 grams per centimeter squared. From what we saw in the previous example, I know my grams are going to cancel out because it's like I'm multiplying by the reciprocal, and I'm going to get something in centimeters squared. So 8.5 divided by 5.3 is greater than 1, less than 2. 1.60, blah, 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 but only 2 sig figs, so 1.6. And this is going to be centimeters squared. That equals r squared. To find r, we need to get rid of the square for both the r and the centimeter squared, so we'll take a square root of each side, the radical. So if we take the square root of 1.6, we get 1.264, which with only 2 sig figs here, we'll just call this 1.3. The square root of centimeters squared is just centimeters, and that will give us r. Okay. If we had a more complicated exponent here, like something to the cube, we might have to take a cube root. If something was to the fourth, then the fourth root, the fifth root, sixth root, whatever this is up here, we'd have to take that proper root of it. And remember, if it was something like a seventh root, that just goes in front of that radical sign. Okay, and if you have trouble like putting those into a calculator, let me know. Sometimes that can get tricky depending on what calculator you're using, but that's how you can do it. You could have also, if you don't like putting the radical sign here, remember, if you take something like 1.6 and then raise it to the half power, that's the same as taking a square root. Or if you raised it to like the 1/7 power, that's the same thing as taking a seventh root of things. Okay, so if you're having, like, that's much easier to do on a calculator because you can just say 1.6 caret to the 1 divided by 7. So if you have trouble with, weird exponents or weird powers, weird radical signs on your calculator, try it this way, see if it works. And if you still need help, like in theory, you'll see me in school, or I can help you out and show you what to do there. Okay, but that's just the end of these notes here. What you're doing, and these are just basic empirical functions. We're just putting in values, keeping track of our units, and doing a little bit of math. Okay, so hopefully that makes sense to you. If you need help, let me know. But for now, we are finished. Adios. Take it easy.